regular. So that means unit regular means that if the flow is smooth and has multiplicity 1, then it can't suddenly vanish. Remember, Ricci flow is allowed to just disappear. Unit regular means if your flow is smooth and with multiplicity 1, then it can't suddenly disappear. Cyclic mod 2 is a weak version of saying you can say what is inside and outside. So you have an orientation. And if you're hypersurfaces, that is what you then that's expected that you can do something like this. But we have also sort of discussed sort of like past singularities. Ricci sort of these weak solutions might not be unique anymore. Okay. Now, one fundamental tool here to understand singularity formation in mean curvature flow is the Mantoulidis formula. Here, the basic ingredient is this backwards heat kernel in the ambient space, where you change the scaling here a little bit. The usual backwards heat kernel would have to here an exponent n+1. We only take n here to adjust it to the dimension of the surface. And you see at the space-time point x0, t0, this here more or less concentrates to a delta function. If you go a bit to prior times, we have a Gaussian with sort of center at x0, t0. Okay. Now, the important computation then is that if you integrate your flowing surfaces against this backwards heat kernel here, then that quantity is monotonically decreasing in time under mean curvature flow. And one of the consequences of this, the first thing what you can do is you can just take that part here, this is now a monotone quantity, and you can define its limit. So this is exactly, you take that quantity, you take final time minus r squared, since time has like scales like space squared, so you take the radius with then minus r squared, would be like a good way. So it's just a formalism here. And then you take the limit as r goes to 0. That's called the Gaussian density. It's like for minimal surfaces, like the density of a minimal surface at the point. For example, all of you have heard about Allard's theorem. If you have a minimal stationary minimal varifold, and you know the density is less than 1 plus epsilon, then you're smooth. Something similar is known for Ricci flows as well. So you can do statements like that. Okay. I already sort of explained this more in my lectures, but let's repeat this here again. So how do we do singularity analysis, especially sort of if you already only have weak flows? So the important thing is you can do parabolic scaling. So you scale space by a factor lambda and time by a factor lambda squared. And the important thing is that if you have a mean curvature flow and you scale space and time like this, it gets mapped again into a mean curvature flow. So what is the most natural thing to do if you have a singularity? So you take a sequence of scaling factors. So you think about, we're kind of like a microscope with sort of the amplification factors. Now we take our flow here. Think of this sitting in space-time. We sort of shift the point we want to look at. We shift it to the origin in space-time. Same as for minimal surfaces. And then we dilate. And if you want to understand the singularity, since this is again a mean curvature flow, we can hope that in some sense we can take a limit here, get a weak limit, and then this weak limit should somehow tell us at least the first order asymptotic of the singularity. And what we have seen in sort of in the lecture in the mini course, that this Ricci compactness theorem gives us enough information to actually pass two limits here always, and get this tangent flow. And then the monotonicity formula says here, okay, this limit, what we get here is self-similar, also is invariant under this parabolic scaling for negative time. That means here that this flow here for negative time, the limit you get here is just always a copy of the minus time minus 1 slice, where you just do the right parabolic scaling. I'll give a few examples now in a moment. So this is like saying for a minimal surface, you do a blow up and you get a minimal cone. Or the same thing if you have an Einstein manifold, you do a blow up at a point, you get a Ricci flat tangent cone. It's the same thing, okay. Now mean curvature flow here is a parabolic equation. Now you see here by this, this sort of has fixed time invariance here, sort of a time scaling here. So this will turn, the mean curvature flow equation will turn into an elliptic equation for this time -1 slice here. And that is exactly, you get a prescribed mean curvature equation. You see, mean curvature is given by the position vector projected to each point to the normal space, and then it is factor -1/2 here. Yeah? So these are sort of these models for singularities. And we had seen in the lectures that they don't need to be smooth necessarily. So they can also be singular. For example, like the union of two planes which intersect each other would be. It's a singular, but it would be still an example of a tangent flow. Okay. Now here's another interesting thing which we'll need later here today. We have all seen sort of this exponent e to the -x²/4. This also appears already in the monotonicity formula. You can check here that this this equation here is exactly the Euler-Lagrange equation of this weighted area functional. If you see, variation of the measure here gives the mean curvature. If you take the derivative which comes from e to the -x²/4, gives you exactly -x²/2. So these shrinkers are exactly all critical points of this Gaussian area. And what you can also see, actually, if you look at this, stare at this closely, you can think of this actually as a minimal surface is in a conformally deformed metric in the ambient space. But you see, this metric is not extremely nice. You see, it's incomplete. See, infinity is at finite distance. You have exponential decay to infinity. So infinity has a very special role here. You'll see this later. So infinity is not so far away. So it behaves differently to what you otherwise think, and what we'll later see as well. In some sense, you can also think about this Gaussian space with this metric. It behaves a bit like a space with positive Ricci curvature. For example, later we'll see that these shrinkers satisfy a Frankel property. If you have a embedded minimal surfaces in a space with positive Ricci curvature, you have Frankel property. Any two minimal hypersurfaces have to intersect. You'll see something like this is also true for shrinkers. So it behaves a bit like actually, in some sense, like some kind of positively curved sphere in some sense, positive Ricci curvature. Okay, what are examples? Here, the most basic example is just a flat plane, going through the origin. That's a self-shrinker. No mean curvature, flat, has to go through the origin because you want to have it to be a cone. Okay, here's the sphere. What you already see, but let me draw you the space-time track. Let's do it this way, maybe. So here we had take time, and it might help with the picture in mind, which is good to develop a bit here. So here's the time -1 slice, and then the space-time track sort of looks like a parabola. Where you see here these shrinking spheres. So here you see this ancient evolution. This exists from time -infinity of the sphere, and here at this point it has the singularity at the origin. So this is a good way to think about it. And here's sort of like, here is m-1, here's maybe m-2. And you see this evolution accelerates actually as you run into the singularity, because the mean curvature starts to increase. And so in some sense, it will later be helpful to think always as flows as sitting in space and time. So here's Rn+1. Okay. Now, if we have shrinking spheres, we can take cross products with RKs, and then we get shrinking generalized cylinders. The most basic example is just sort of a standard shrinking cylinder. Now let's draw this also in space-time. So we have this here of time here. We have here this shrinking cylinder. And you can see, so this shrinking cylinder, just want to point this out. This will at time 0 converge to a line here. It's like a parabola across R. Okay. Now, here's the first interesting fact. Now, you can ask yourself here, if you start with a surface which has initially mean convex, so positive mean curvature, so the surface is moving to the inside. The very initial, just take it strictly positive. It's moving to the inside. Now you can take the avoidance principle and you see that the flow, if you translate the flow in time a tiny little bit, it has to avoid itself. And because if it avoids itself initially, then you use the avoidance principle, you see the flow will keep avoiding itself for all positive times, if you just shift it a little bit in time. But the idea is, you can take a limit and differentiate that condition. And that condition will just tell you that the mean curvature, non-negative mean curvature, is preserved. So in some sense, you can see non-negative mean curvature as an infinitesimal version of the avoidance principle. You can actually see if you have any flow which satisfies an avoidance principle, then also sign on the speed has to be preserved, because it's just a differentiated version of the avoidance principle. Yeah. Okay. And what Huisken showed is that if you are in this case to have non-negative mean curvature, then these are the plane, which is sort of the regular points where you have no singularities, shrinking spheres and shrinking generalized cylinders are the only singularity models in this case. Yeah? And okay, here's already sort of another example here. Was an example by Angenant, yeah, that there are, you can just not drawing space-time here now. So there's a torus revolution here, yeah. We just revolve here. So it's not a round sphere, yeah. It's a bit more egg-shaped. And so there's a torus which shrinks down to a point in finite time. Yeah? And now we can try to imagine how this space-time tract looks like. Yeah, it's sort of like a torus, yeah, which someone starts pulling down on kind of a parabola shape. Yeah? Or can you think of like the outer boundary here? Yeah? That bit is like in a parabola, the inner bit, and you connect them with the torus. Yeah? So this is sort of how you would see this. Yeah? And now here's sort of an interesting question. Yeah. Now you can ask yourself, can I construct other shrinkers? Yeah. So here's a singular shrinker, for example. You just take the plane to the origin, yeah, and you intersect it with the sphere. Yeah. Yeah, so this is in some sense a singular shrinker. Okay. But we have seen before that this is so remember the equation was mean curvature is equal to x comma nu over 2. So it's a prescribed mean curvature equation. And you all know constant mean curvature surfaces, and you know if you have two constant mean curvature surfaces with the same mean curvature, which intersect transversally, then you can usually desingularize by kind of gluing in little towers of little like Schurke surfaces. We drill in little holes here and glue in Schurke surfaces. So this is what Capoleas, Klein, and Möller and Nguyen did. And here's a picture. So this is how something like this would look like. Yeah? So you see, here's the plane. You don't see the part of the plane here in the middle. That part we don't see. Here's the upper part of the sphere, and here we look into the lower part of the sphere. Now, so if you look from the side, this would look like this. Okay, so we have here these holes where we can look into. Then there's these other holes which go the other direction here. Yeah? These are kind of these ones here. Yeah? So at the moment we look in through one of these holes, yeah, and we see the bottom here. But there's one interesting effect, which turns out exactly sort of that sort of infinity in this Gaussian space is not so far away. Yeah? If you think if you want to do this desingularization here, this you think would be kind of when you glue in the Schurke surface, this should be a local problem. At least for CMC surfaces, it's a local problem. Yeah. Just do your perturbation decays as you go out to infinity. It's a local perturbation. Get a high genus here, but it turns out in this work of Capoleas, Klein, and Möller and Nguyen, that to do this desingularization here, they had to change this cone at infinity. So it's not a plane here anymore at infinity. So this cone here at infinity is wiggly. It's kind of like sinusoidal, I guess. Yeah. So there is actually exactly so this infinity here is not so far away. If you want to do this perturbation here, you have to change infinity. Yeah? So this Gaussian space behaves very different to sort of a non-compact space otherwise. Yeah? Okay. So now there's another consequence of this. So the cone here, that's not flat R2 here, this asymptotic cone here. But you see, if you think of the space-time evolution, remember before this picture of the sphere, of the cylinder. So that goes to the line here. that shrinks down to the line. Yeah, if you let this here evolve at time 0, it will exactly evolve into this asymptotic cone at infinity. It just gets scaled down, and the time 0 slice is this cone at infinity. Yeah? So, okay, so here's maybe a bit about the structure of self-shrinkers. Okay, so this is what I first said, yeah. Okay, so let me draw a picture maybe here, yeah. That can be very instructive, yeah. So you have again here Rn plus 1. And you have here one straight direction. So this is the time here, yeah. Now, let me just draw this here now. For simplicity, I'll draw network flow because that at least can draw, yeah. So, for example, shrinker network flow. This is one dimensional, would be like something like this. Yeah, think of this actually. You know, this should represent the topology. Yeah, these are the ends. Yeah, and now at time 0. Yeah, so this will shrink down. This will become smaller. Again, this is the space-time track here. Now I'm just drawing the slices, but at time 0, you'll just see this cone here. Okay, so you see for the time -1 slice, the cone at infinity then becomes the time 0 slice in its evolution. So that's where the flow is flowing into. It flows into its asymptotic cone. Now I've seen before the sphere shrinks to a point. Okay, yeah, that's the asymptotic cone. Yeah, the cylinder shrinks into a line. Yeah? Even if it's lower dimensional, that's the asymptotic cone. Yeah? Okay, so this you can always prove. This is always true in a just Hausdorff distance sense. Yeah? This just you get out of the monotonicity formula. Now let's look at these examples here. Yeah? Let's say, okay, we call a shrinker asymptotically conical if this cone is smooth at infinity. Yeah? So if it's a cone over a smooth submanifold of Sn. Then we say that the shrinker is asymptotically conical if this cone at infinity is smooth and the convergence to the cone is smooth. Yeah? So it also means no higher multiplicity. Yeah? Okay, so that's an asymptotically conical shrinker. Now here the interesting properties here. So there's very important word of Lu Wang from 2014. It says if you are in this asymptotically conical case, so then actually the cone at infinity determines the shrinker uniquely. So what does this mean here? So this means sort of this cone here at infinity, there can only be one shrinker asymptotic to that. Yeah, I remember this was this picture. This is what I said. This is why this can't be flat. Because if it would be flat, it would have to be just R2. So it has to be wiggly. Yeah. Okay. Now, what is the idea of Lu, how to prove this here? So the idea is this picture actually. So you see, you have the self-cylinder evolution, and it evolves into the cone. Assume you have two solutions with the same asymptotic cone. So you would have two solutions flowing into the same, let's say if you're away from the origin here, everything is nice and smooth, yeah? It flows into the same smooth hypersurface. Okay, and now if you know parabolic equations, there's something like backwards uniqueness. You can't have that a solution to a parabolic equation, that two solutions evolve into the same time slice at a future time, but they're not equal at previous times. Okay, so what Lu was able to prove, that she used a localized version of a backwards uniqueness result to say, okay, if two solutions flow into the same cone, then they have to be equal. Yeah? So this is this idea here, yeah? But it needs kind of this further regularity. So this cone here has to be rather regular and smooth to get this very general uniqueness result. Okay, the other very important result from Lu is that if you're in R3, you're two-dimensional with finite genus and embedded, then the shrinker can have only cylindrical or smoothly conical ends. So this means, okay, so maybe before I continue, are there any questions so far? Okay, now let me draw your picture here. Maybe I can even give you an idea why this is actually why you would expect something like this. If you hear this the first time, you think, okay, where does this come from? Huh? Okay, but again, it's important to think about this geometric picture here. So you have this flow here. Okay, so here's time, here's Rn plus 1. And I'll draw now the cone at time 0. Yeah? So I'll do this in a bit different. So here you have a smoothly asymptotically conical end. Yeah? Maybe here another one. But maybe you also have a cylindrical end that would be just a line. Yeah? So how would your shrinker look like? So your shrinker would maybe sort of at the time -1 slice sort of be asymptotically conical here, have another end down here, have here maybe some topology, yeah? And here it might have something which is asymptotic to a cylinder. Okay. So you look at this evolution. That's why it flows into. Now what you can do here, you can look at this flow here and do a tangent flow around that point. So you rescale around that point. But you see, you have here a cone. So what you get as a result is that the tangent flow here will split a line. The tangent flow splits a line, but then you have a two-dimensional self-shrinker which splits a line. So the cross-section has to be a one-dimensional self-shrinking curve. But all the one-dimensional self-shrinking curves are classified. I guess you have all seen this. So this is either the only embedded ones are the round sphere, the round circle, and the line here. There's nothing else. There's some non-embedded ones. I guess you have seen these kind of like immersed ones. But these ones we don't need to think about. Because they're immersed. So this means you go here, you look at the tangent flow, and the tangent flow splits a line, and the cross section is either a line or a circle. So you see, this is the case when you see a circle. The cross section is a circle. And this is the case when the cross section is a line. Because if you see at one point that the cross section is a line, you can go around and always have to see a line. Because if you would see a circle, everything would have to be the circle already. So the main work then of Lu was actually to prove that this whole tangent flow here happens with multiplicity 1. Because that you can't rule out initially. So she was able then to prove in this special setting that these tangent flows happen with multiplicity 1. And then you can just use these arguments. And by these arguments, you can understand what the asymptotic cones are. So in some sense, looking at this parabolic picture is in some sense gives much more insight than actually just thinking of the shrinker and just scaling it down. There's parabolic behavior hidden in scaling down. Okay. Now, Ilmanen actually conjectured that this here cannot happen. So this is more or less a strengthening of this result of Lu Wang here, in the asymptotically conical case, that also if you're asymptotic to a cylinder, that you also have uniqueness, that you have to be the cylinder. So that would be the cylinder uniqueness conjecture. But it turns out, you see, this cone is much more degenerate. So the asymptotic there is much, much harder. So several people have tried. Lu has a result sort of with very strong asymptotics. But you don't, it seems to be a very hard result to prove. But it's conjectured that you can't have cylindrical ends if you embed it in dimension 2. If you're not only the cylinder. Okay, and here's another result of Simon Brendle. So assume you have an embedded genus 0 shrinker. So you think of an embedded sphere, or an embedded cylinder in R3. And as I have explained to you, you can think of this Gaussian space. So these are minimal surfaces in the Gaussian space. And these are embedded. And there is a previous result of Antonio Ross, who shows that if you have an embedded minimal 2 sphere in the 3 sphere, then it has to be an equator. This is the result of Ross. What Brendle realized is that you can generalize this proof idea of Ross into this case, because this Gaussian space also behaves like more or less like a sphere, or like a space with positive Ricci curvature. And what said, okay, that actually this picture here, this is why I drew, for example, here topology. So if you have no topology, then you can only be a sphere or a cylinder. So this is this result of Simon Brendle. And it uses again the structure of this Gaussian space, that it behaves somewhat like a space of positive Ricci curvature. Okay. Now you've seen here, this is a whole zoo of singularities. Yeah? There's sort of no hope of classification. We maybe can classify n's. Yeah? We hope that we can at least sort of say something about n's. Yeah? But on the other hand, if you have these spherical and generalized cylindrical singularities, much more is known. Yeah? So by work of Colding-Minicozzi, there's a very good regularity theory. You know much more about how big your singular set is, even for a weak flow. Yeah? And we have said before also, then more or less like the idea is here, when you have a singularity which is asymptotically conical, what you can show is that the forward evolution out of such a cone here, assuming that this end wouldn't be here, that can be non-unique. And that is then something which might sort of in the flow cause non-uniqueness. So you have a singularity which is modeled on some of these asymptotically conical guys, and then after that singularity, you have a singularity formed which has conical structure, and then there are actually non-unique evolutions out of this cone, which gives you possible evolution of your whole flow going through this singularity here. But in contrast, what Hershkowitz and White sort of, and together with more recent result, and this is the proof of this positive mean curvature neighborhood conjecture, what they proved is that if you only have spherical and cylindrical singularities, then actually you have uniqueness. And more or less locally, what they prove is you have positive mean curvature, you have motion in one direction, and that gives uniqueness. So weak evolutions through these singularities is unique. So it's very good if you get only these singularities. Okay. And also in general, you have very little control on the size of the singular set, and as I said, possibly non-uniqueness if you have this general singularities. Okay, now there's an old conjecture of Huisken, who somehow conjectured that a generic mean curvature flow has only these kind of spherical and cylindrical singularities. The question was still, what does generic mean? What sense of generic? Okay. Now, there was first fundamental work of Colding and Minicozzi, which they looked, and I'll explain this in a moment. They showed that you can somehow sort of get a good sort of setup what means linearly stable for a singularity. So they sort of showed that sort of the only linearly stable singularity models are spheres and generalized cylinders. Sort of on the linearized level, sort of spheres and cylinders should be the only generic ones. So they proved in the linearized level, these are the only generic ones. Sort of all the other ones are unstable. They're more or less, all the other ones are unstable. If you look more or less at these as these minimal surfaces in this Gaussian metric, and I explain in more, then there are some natural instabilities which just come from translation and scaling. These you can mod out. And if you mod out these natural instabilities, which every minimal surface in this Gaussian space has, then modulo these natural instabilities, the only stable ones are spheres and cylinders. And all the other ones have other instabilities. Now, what they did is they said, okay, if you have this linearized understanding, so they say if you have a compact singularity model like the Anjonen torus, then the linear information is strong enough to say, okay, assume the singularity is forming, you see an Anjonen torus forming, you stop the flow a little bit before the singularity forms, you perturb the flow a tiny little bit where you use the linear information, and then you can make sure your flow will never run again into this Anjonen torus. And so they did this a priori assumption that they say, okay, assume you have only compact singularity models, which is highly unlikely. Then you can always do this kind of stepwise perturbation. Now, the question is sort of how can we perturb away non-compact singularity models like asymptotically conical shrinkers? Or is what we actually would like to do to say, okay, we want to only perturb the initial condition. We want to say, okay, we wiggle the initial condition a tiny little bit, and then we make sure that there are no other singularities, non-generic singularities. What we would really like to do is make this even work past singularities. So you have a first singularity, you wiggle a little bit, you avoid it, But now, your flow has had singularities. There could be another singularity forming, but that could be a non-generic one. Now I want to go back to the initial data, wiggle the initial data a little bit more, and make sure that although I already have one singularity, that the second one after that is also avoided. So that's what we would really like to do. Okay, now here are our first results. So it's for mean curvature flow in R3. So let's take a closed embedded surface. The statement is then as follows. So we can take an arbitrarily small C infinity perturbation of this initial surface M, so just a C infinity graph or M prime over M, such that the following holds. So either we have the optimal statement, so either this little perturbation we get exactly what we want. The weak flow has only multiplicity 1, so no sheeting, spherical and cylindrical tangent flows, really generic. We really wiggle the initial data and get what we want. Or what we can't rule out at the moment is, it might happen that there is a time, and there's a tangent flow of this flow M prime here, such that, okay, we might have higher multiplicity. This is still a very big open conjecture in mean curvature flow, at least in dimension 2 embedded. That should be ruled out. So this hasn't been done so far. So it has higher multiplicity. Or you have this example, what I said before. So you have a shrinker which has a cylindrical end, but it's not a cylinder. These two scenarios which you can't rule out yet. And as we said before, both of these scenarios here are conjectured not to exist. So the one is the cylinder uniqueness conjecture, the one is the multiplicity 1 conjecture. If these conjectures are true, then our result says, okay, you can really just wiggle initially the initial data and you get a generic flow completely through singularities. Everything is just neck pinches and so like more or less you get what you then get for Ricci flow in dimension 3, which is then very good because then you can start to track topology and stuff like that. Okay, as I said, the important thing is we only need to perturb the initial condition, and we are able to perturb away these asymptotically conal tangent flows and compact ones. Okay, now let me start to give a bit an idea sort of how to prove this here. Okay, the idea is it relies on this avoidance principle. So this is our initial surface M0. Okay, now we can just say, okay, we can even assume that this weak solution is unique starting at M0. We have seen this sort of just by looking at the level set flow, we can assume that the level set flow of M0 does not fatten, so which is a generic condition. So we can just wiggle a bit and make M0 that the weak solution is unique. That is generic, that you can do. So we have this weak mean curvature flow starting at M0. Now what we do now, we embed M0 into a foliation. I'll just take equidistant surfaces, a small tubular neighborhood which we foliate by equidistant surfaces. We parameterize these equidistant surfaces by a parameter S. Okay. Now we can let all these surfaces MS flow by mean curvature flow, and so we get these weak flows MS starting at this initial data. Okay. Now what do we know now? We know by the avoidance principle that these weak flows still have to avoid each other. So we get more or less a foliation of flows around our initial flow. So we can foliate the whole neighborhood. Now, the best thing is to think about space-time now, about this picture before. So there's a whole foliation of flows which sort of foliates a neighborhood in this space-time picture. Okay, and that uses the avoidance principle that you can do this. Now, what you do now, so assume we have a singular point of our initial flow. What you do again, this is the singular point X. We shift it to the origin, just shift the whole space-time picture that the singularity is there. And we want to analyze the singularity. So we blow up by a sequence of rescalings here and get a tangent flow. Okay, and now we assume this tangent flow is something that we don't want to see. Okay, but what we can do is, you see, we can now pass this whole foliation to a limit simultaneously. So we have fixed now our origin in space-time, but we have this foliation around that, and we now blow up the whole foliation. We'll see less and less of the foliation. But we can somehow hope that, as we blow up here, that's, maybe this foliation, what we'll see then in the end, with very high curvature, that it might get canonical. That this is sort of not anymore arbitrary. Okay, so what you can do now, you can choose this sequence SI here. You see carefully as it goes to 0, as you do this blow up, then you look at these works. What you do is you choose this SI, that this flow here has always distance 1 to the origin in space-time. That's the idea. If you take distance 1, then after taking this limit of rescalings, you will see something. It has not escaped. There is something, but you see what you get here. This converges to a flow which is on one side of this tangent flow. Think of this tangent flow, this picture we had before in space-time. Now you get a flow which sits on one side of that, either the inside or the outside. But it's not self-similar. But the important thing, it's on one side of this flow and it's ancient. Because this flow, this limit will also have existed then after blowing up for all negative times. So let's maybe draw your picture here, what we had before here. So here we had this, so here's this asymptotically conical guy. Maybe here have some topology. Here's the time axis. This will be the cone at time 0. A bit hard to draw now. Now, what are these flows here? So this is like a flow which sort of lives on the outside of this here. And in the end, it will somehow be somewhere on the outside of this here, of this cone here. See? That's the idea. But this flow is ancient. Because we have scaled up everything. So it's not self-similar, but it's ancient. Okay. Now, the aim is now that the idea is this guy, what you see here out here, this guy is unique up to parabolic scaling. So this is the idea. This limit you get is unique up to parabolic scaling. And what we want to prove is that this guy, I'll explain you why we can expect this. This guy has only good singularities, only spherical and cylindrical singularities. So what is, now the idea is then if we can prove that this flow here on the outside of it, that this is very nice, has only generic singularities, then the idea is then if we look at this blow up sequence here, then we maybe can argue that already far enough down on this sequence, our flows have this good property. They only have generic singularities. So that's the idea. So we prove that the limit here, that this guy is unique, has only generic singularities, and then here down the sequence, already far enough down, we can do an argument and say then we only see generic singularities there. Okay, so if you can do this, now you choose this SI right, and then we can maybe perturb away the first singularity. Okay, now we change this parameter S slightly. We let this flow further. We might run into another singularity, which is non-generic. Okay, but we can perturb that guy now again. We do a second perturbation. Perturb that guy away. Perturb the first perturbation again. Now, if you first think about this, you think, okay, now if you want to continue this, you might have to do infinitely many perturbations. Because if you perturb away the first, perturb away again, where do you know from that this that this doesn't accumulate? And the idea is as follows here. If you have two-dimensional surfaces, you can prove here, this is this idea here, you can prove here that this guy here actually is star-shaped here at time 0. That's what we can prove. This is star-shaped here at time 0, this flow on the outside, and it has no genus. So this guy has genus, that we know by the result of Brendle. So this guy will have genus at large negative times, but to go from here to here, it has to lose genus. So there's something lost in this perturbation. And when we have to now do successive perturbations, we can argue that each time we lose genus, so you only have to do finitely many perturbations. That's the idea why finitely many perturbations, why we don't have to why we don't get accumulation when we do these perturbations. Okay. Now let me Okay, so this is this idea why you then can sort of hope in dimension 2 to really perturb further and further and really get through. Okay, now let me explain a bit. So the idea is now, how can we now hope to, now, okay, if you come up with this, you think, okay, how do I get a handle on proving that this guy might be unique? Okay, that's what I want to prove now. This flow on one side here, that might be unique. Okay, now here's the idea. Okay, now this was the assumption before. Now this was our initial flow here. This was the singular point we looked at. That was the tangent flow. Okay, we assume it's multiplicity 1, and the assumption is now we said, okay, the cases we can treat is that it's a compact shrinker like the Antonin torus, or it's asymptotically conical like this example of Capuleas, Klein, and Möller. Yeah. Okay. Now, what you can do, you see there's a natural scaling in here. No? And you might have seen this for mean curvature flow. You can just, you try to sort of, you rescale the flow, you want to take out that scaling. Same thing for Ricci flow. Yeah, what you do now for mean curvature flow is you scale time and you scale space. Yeah, that is exactly taking out the square root of t behavior. So this would make a shrinker for this flow here. A shrinker becomes a stationary point. Yeah, and if you do this here, this gets a flow where the normal speed is exactly mean curvature plus x perp over 2. You see a shrinker is stationary. So you make the shrinker stationary. But you see this flow on the outside, you can also rescale it like this, and you get a flow now which in this rescaled picture, this is, you have here the shrinker. Yeah? If you're the shrinker sitting, yeah. Now this is stationary, and now this outside flow will be something which just lives out here, or inside, just on one side. Yeah, but if you also a very thin neck, yeah. Okay, that's this flow now in this rescaled setting. Yeah, so this guy is fixed now; it's not moving, and we have only this guy moving here. But it's not anymore mean curvature flow, but it's mean curvature flow with this forcing term. Now, important thing to note is that this flow is up to a conformal factor is mean curvature flow in this conformal metric, which we had looked at before. And we know that this flow here lies on one side of this now fixed shrinking self-shrinker. Okay. Now what we want to prove is that as we go for this rescaled flow back to time minus infinity, that flow converges from one side exactly to the same shrinker. So how do we do this? The idea is, yeah, this flow m bar for the usual monotonicity. Remember, it's an ancient flow. So the monotonicity formula allows also to take a tangent flow at minus infinity. So you do a blowdown. Like if you have an entire minimal surface, you can also do a blowdown and get a minimal cone. That's the behavior at time minus infinity, or at infinity. If you do this here, this is the same thing as for this rescaled flow to go with tau to minus infinity, you get another self-shrinker. Yeah. So this means in this picture here, this flow here, as you go with tau to minus infinity, will converge to another self-shrinker. So a minimal surface in this Gaussian metric, but this minimal surface, hypersurface, has to lie outside, so it can't intersect. Either it's equal, or we don't know this, but it has to lie on one side of this shrinker, because the whole flow is on the outside of this minimal surface here in this Gaussian metric. And now the important thing is, as I said before, there's a Frankel property for shrinkers. Any two minimal hypersurfaces in this Gaussian space have to, so either they're equal or they have to intersect. But this guy can't intersect the other one because it lies on one side. Strong maximum principle has to be the same guy. So this means this flow here on one side converges back as you go to minus infinity to exactly the same shrinker. So we have a flow which on one side comes out of a minimal surface. Okay, if you think about like mean curvature flow, or like you have a stationary point and you have an ancient solution coming out of a stationary point. That usually has to sort of go in sort of an then this usually means that this minimal surface has to have index, so unstable directions, and some of this flow has to go sort of move in an unstable direction for the second variation out of that minimal surface. Okay, Now, the idea is, okay, so this gives then an ancient flow emerging to one side out of this minimal surface here in this Gaussian metric. But one side, you see, it moves to one side. If you think about the eigenfunctions of a minimal surface, there's only one eigenfunction which has a sign. That's the lowest eigenfunction. So if you have the motion to one direction, the behavior should be governed by the smallest eigenfunction for the smallest eigenvalue of the second variation. But this function has a sign, so the speed has a sign. So this is what we're then able to, so this one-sidedness that it comes from one side, this we use to prove that the behavior is dominated by the first eigenfunction, which goes in one direction. That allows us to prove using PDE techniques. This goes back to this work of Choi and Mantoulidis, where they did it for minimal surfaces, to prove that for large negative times, we can argue this flow is smooth actually for large negative times, and it's unique. Because we can pin down the first order analysis. We can pin down the first order analysis, and that's enough to make this, to prove that this flow is unique for large negative times. Are there any questions? Okay, and now here's sort of the result. So we have pinned down the flow for large negative times. And what we get is that the speed here, if you take this, if you look at the speed here, h plus x comma nu over 2, that this speed is positive, has a sign. But you see, this is a good replacement for mean convexity. You see, if you have a singularity forming, this is a term which blows up. That term won't blow up at a singularity. So more or less, the singularity forming is really mean convex, more or less. Okay. And now we can use this to prove that, okay, assume you have a self-shrinker, either compact or smoothly asymptotically conical, then there is only one unique ancient solution to mean curvature flow on each side of it, which is this joint there. And we need an entropy condition. So this rules out, I'll explain this in a moment, this rules out higher multiplicity, but that's something we can always attain. And the important is, so this is a weak flow actually. So this is a flow with singularities, but this flow is shrinker mean convex. So this flow has that speed bound, it goes to one direction. But the shrinker mean convexity, that's exactly what, as I said, remember this result of Huisken before, if you mean convex, you only get generic singularities, So we can prove here, extend results of Brian White, that this weak flow is unique and has only, in a weak sense, always generic singularities. Okay, so in some sense, so what is maybe a picture here? It's instructive to look at this before my time runs out. Look at this example here. You see, this is like a CMC surface. So these necks here somehow have to be rather balanced. There seems to be some force balancing here. What you can imagine now, you make these necks a bit thicker, so you make these necks a bit thinner, these necks a bit thicker. If you do this, this should destabilize this guy. So you can do a perturbation where you perturb just to one side. So this destabilizes these necks. So you can see this ancient solution on one side as a canonical destabilization of this highly unstable configuration. Okay, so this is this here, for people who know minimal hypersurfaces more, this is, for example, there's work of Hart and Simon and Smale, where you have area minimizing hypersurfaces in R8, which can have isolated singularities. Then they argue that you can perturb them away. And what they use exactly, they use sort of one-sided foliations of area minimizing hypercones. This is their central tool. So more or less what we have here is the parabolic analog. There they are smooth. Here we don't get smoothness, we just get that it has generic singularities. Okay. Now here is a bit of strengthening. This is a bit more for the specialists. Okay, so this weak flow on one side, has only generalized multiplicity 1 generalized cylindrical singularities, spheres and cylinders. As I said before, this flow we then get, so this is exactly this condition, what we get is then later is that 2th plus x comma nu, that this is greater or equal than 0, but you see at time 0, that term goes away. That means x comma nu is positive, that's star-shapedness. So at time 0, that flow is smooth and star-shapedness, especially as no topology. What you can then prove for if you want to understand sort of future evolutions, you can prove actually that this flow converges to one of these outermost expanders coming out of this asymptotic cone at time 0. So it's also a way sort of to interpolate sort of to get this whole evolution to the future time as well. Okay, now in the last few minutes, let me state some more results here. Okay, so that's what I just said already. Okay, here's a little bit about entropy. So this is this quantity entropy that Colding-Minicozzi introduced. It's more or less the quantity from the Mantoulidis formula, where you're now just allowed to take any possible future base point. You can think of this, it's the same thing as modding out the Mantoulidis formula by translations and scalings. Shifting time is the scaling change, and shifting the base point is a translation. And what they then showed is exactly that these shrinkers are, they looked at the stability with respect to this function, or to understand sort of linearized stabilities for the shrinkers. But you still get here, just trivially, it's like Perelman's mu entropy, that this is still monotonically decreasing under mean curvature flow. Now, you can see this here, you can think about, okay, that should be kind of some kind of measure of complexity. And you can first check what happens on shrinkers. So you can check actually the sphere. There's the first, with the very lowest one is the plane with equal to 1. Lambda is equal to 1 on a plane. Then you get the round sphere, and then you get all these cylinders going up to, in the end here, S1 cross Rn minus 1 is the highest entropy. Now, for example, Colding, Illman, Minicozzi, and White have shown that the round sphere has lowest entropy among non-planar self-shrinkers. And Bernstein and Wang and Zhu have proven that the round sphere has lowest entropy among all closed hypersurfaces. And so what Bernstein and Wang proved is that if you just look at shrinkers, so these first two steps in R3, so the lowest one is S2, and the next one is S1 cross R, and there's no other shrinker in between. So there's no other singularity model in between. So there's a gap here between these two. There's nothing else. And now you can ask yourself a similar thing in R4. What, for example, Bernstein and Wang proved is like if you're below S2 cross R, so this would be the first lowest one after the sphere in R4, then you know you're already diffeomorphic to S3. But what was still open is that if you're possibly isotopic to R3, this would be then the Schoenflies conjecture, at least under low entropy. Okay. Since time is running out, let me quickly skip this result in low entropy setting here. Maybe go to some more of the results here. So what we can prove is our result. First, sort of let's state this this consequence here. So if we have a three-dimensional hypersurface in R4, and we have entropy below the first step. The first one would be S3, then is S2 cross R. Then we can actually prove that, so there's no gap theorem known in R4. That's not yet known. So there could be shrinkers in between the sphere and the cylinder. But we can prove that we can do a small perturbation so that the flow remains completely smooth until it contracts to a point. And what this gives an alternative proof of this result of Bernstein and Wang, that you get this low entropy Schoenflies theorem. So you can really perturb here. And so if your initial hypersurface has entropy less than S1, S2 cross R, then you're smoothly isotopic to the round S3. We published this the same time as they published their result. But here's another interesting consequence now. I did skip this here. So we can do also the, in R4, we can actually do this generic perturbation in this low entropy setting. One setting, we can go up to S1 cross R2. to get generic flows. Yeah? Now there's a PhD student of mine, Josh Dennis Holgate, who proved if you have such a generic weak flow with only, then you can approximate it by flows with surgery. So you can use the information about the weak flow and the limit to actually really do surgery and approximate it by surgery. What is the consequence of this? It's like if you have now a three-dimensional hypersurface, should be R4, sorry, homeomorphic to S3, and it has this one better entropy bound less than S1 cross R2, then the weak flow still could have cylindrical singularities. Then you can approximate it by surgery, and then you can actually get that the initial surface is smoothly isotopic to the round S3, because you can just do surgery and understand what happens topologically, and you can never cut a handle or anything like this. Okay, let me stop here. Thank you very much for your attention.
Thank you very much, Felix, for this nice lecture. There are probably lots of questions.
Can I ask a question?
Sure.
Felix, so in your perturbation, so do you only consider parallel hypersurfaces?
No. This was just an example. They have to be to one side.
Okay.
So you need to go to one side, but they don't need to be parallel.
But it's possible. So among the parallel ones, you find one which
you would find one.
Okay. So it's really.
But it's only parallel, only initially parallel. Later it doesn't stay parallel.
Yeah, sure. Clear. Yeah.
It's only initially we can take, there. Yeah.
Mm-hmm. Okay. Thanks. Yeah, another question is, so you were mentioning that so that once you have enough control, then you would be looking for topological applications. So these were the ones you have discussed on the last slides, or
exactly. For example, that would be one. This last slide. So you see, now you get this information out of this weak solution, then you can approximate by surgery. There's always the question.
Mm-hmm.
And then this would be the first example of a topological application, where you now know, okay, you assume you're homeomorphic to S3, so you can do surgery. You never cut a handle,
Mm-hmm.
So you always just do disconnect sums, and then in the end, you see, you can put everything back together, So in that sense, now you can start to use that too.
Mm-hmm. Thanks.
Yeah.
Thanks. Any other question? There is a question in the chat.
Okay. I guess Lucio, you mean for the shrinkers, it's a discrete set. If the ends are nice enough, so assume if you only have cylindrical ends, no asymptotically, if you only have asymptotically cylindrical ends, then this is known. You can use this Voyasevich inequality I proved with Otis. Voyasevich gives you that all your levels, that any other shrinker close by, if there is another one, that one has to have the same value. So that would give you a discrete set of values in R, at least for low. So it's harder if you have more general ends. So more or less, as soon as you get Voyasevich working, you would only get a discrete set of values. Is this clear? It's like, entire, I don't know, higher multiplicity, I don't know. But you see, Voyasevich says that you have f of surface M minus f of sigma is to the power 1 minus theta, hope I may not make a mistake, is less than grad f in L2. Okay. But if you have another shrinker now, we're close by, being a shrinker means that term vanishes. So this means the functional has to have the same value. So that gives the discreteness. Now higher multiplicity gets difficult, different ends get difficult, but at least you could hope something like this could be true.
Thanks. Other questions? But still.
Yeah. So you see type 2 singularities. Yeah, I would expect that you could use something like this, that they are non-generic, because in some sense, if you have a type 2 singularity, you still have a tangent flow. Type 2 singularity would mean that your tangent flow is non-smooth. But now if you understand how to perturb away non-smooth tangent flows, then you would get, and then you can make, then you could hope that they are regular enough to, at least in some setups, then you don't get type 2 singularities. Now sure, higher immersed is something very different, but at least in codimension one, in codimension one, it's still the problem like with the degenerate neck pinch. You could have a degenerate neck pinch, which is still a type 2 singularity, but maybe you get enough information to argue that you then maybe also can perturb that away. It's a very good question. I would be worth trying to see if one can do this. If can more or less can make degenerate neck pinches non-generic, which should be true.
Okay, it seems that there are no more questions. So thank you very much, Felix, for this lecture.
Thank you. Okay. Yeah. Okay.
And take care of yourself. We'll see each other sometime.
See you soon. Bye, everyone. See you soon.